Okay,
Theta is 8 pi over 3. Then what is the sine, cosine?
okay, we want to find the values of all of our trig functions of 8 pi over 3. So there's just two things that we need. We need to know the quadrant this angle lies in, and then we need to know the ordered pair at that reference angle. Well, when we have things given to us in radians, the reference angle is right here. So pi over 3 is our reference angle. That's only true if your fraction's in reduced form. If your fraction's not in reduced form, then put it there first. So what is the ordered pair on the unit circle at pi over 3? Or if you need to think in terms of degrees, how many degrees is pi over 3? 60 degrees. So pi over 3 is the same as 60 degrees. What ordered pair are we talking about on the unit circle? 1/2, and square root of 3 over 2 is our ordered pair on the unit circle. Dr. Kim. The reason that's important is on the unit circle, R is 1. And so our ordered pair lists for us the value of the cosine and the sine. Our x and y are the cosine of the angle and the sine of the angle. So that's the first thing we had to know. What is our reference angle in this ordered pair? The second thing we need to know is the angle given is in which quadrant, because then we just adjust the plus and minus for the trig function. So how do you figure out what quadrant 8 pi over 3 is in? What quadrant is the terminal side of this angle? And why? Well, it's more than one lap around the unit circle, because how long is one lap all the way around? 2 pi. So if I wrote that as something over 3, 2 pi is the same as 6 pi over 3. So this is beyond 6 pi over 3 by 2 pi over 3. 8 pi thirds is equal to 6 pi thirds plus 2 pi thirds. So that's one lap around the circle, and then 2/3 of the way of pi. If the whole circle is 2 pi, the top part of the circle is pi. So 2/3 of the way puts us in which quadrant? Quadrant 2. Which trig functions are positive in quadrant 2? Sine and the cosecant, right? Is that locked? I thought I unlocked it for the whole class. Yes, I didn't. So in quadrant 2, everything's negative but the sine and the cosecant. So we're looking at these ordered pairs. How far can I go over? Go that way. And so the sine of 8 pi over 3 is the y coordinate over there. Square root of 3 over 2. The cosine of 8 pi over 3 is a negative 1/2. You know the cosine and the sine, how do you get the tangent? That's right, divide the y by the x, divide the sine by the cosine. So we take square root of 3 over 2 and divide it by the negative 1/2. The halves will cancel, leaving us with negative square root of 3. Now start flipping those over to get their reciprocals. The reciprocal of the sine is the cosecant. The reciprocal of the cosine is the secant. So that's just going to be a negative 2. and flip the tangent over to get the cotangent. So I get -1 over the square root of 3. So notice they're all negative except for the sign and 1 over the sign. So a bit of this is memorization. Get to know the ordered pairs, at least they're in that first quadrant, and then be able to figure out what quadrant the given angle is in. Does that make sense? So let's try another one. Let me make a bigger numerator. How about let's do the exact same thing using, okay, we did a third. Let's do the same. Do the same for 55 pi over 4. So 55 and 4 have no common factors. That means my fraction is simplified, even though it's top heavy. We can figure that out in a minute. But that means that your reference angle has to be the pi over 4. What's the ordered pair at pi over 4? Both of them are square root of 2 over 2. That's the line y is equal to x. So that's our reference angle. Our ordered pair is this one. So there's the sine, the cosine and the sine. Remember, cosine is x, sine is the y. So the next task is to figure out what quadrant this is in. Well, that's got a lot of 2 pi's in it. So how am I going to quickly find out a quadrant for this one?
4 over 4 plus 1 over 4.
Okay, 4 goes into, let's just see how many times 4 goes into 55 altogether. So that leaves me 15, and then 3 times 4 is 12. So that says it's 13 pi plus 3/4 pi. The 3 is the remainder, the 4 is the divisor. We're all doing this in multiples of pi. So where would one find an angle of measure 13 pi? It's going to be the x-axis. It's going to be the negative x-axis, right? Even multiples of pi. Even multiples of pi would be here. Odd multiples of pi would be here.
Oh, yeah.
So 13 pi is going to land here. So far, I've taken several laps off, and my angle is right here. And now I've got the rest of the circle here that I need to cut up into 4 equal pieces and take the third one. So here it's cut into 2. So 3, 4. There's our angle right there. 13 pi plus 3 pi over 4. So this has to be a quadrant 4 angle. Which trig functions are positive in quadrant 4? Which one?
Tangent.
Not
Cosine.
cosine and secant. Quadrant 4, only the x is positive, y is negative. So cosine is the first member of the ordered pair. Sine is the second member of the ordered pair. Quadrant 4, cosine and secant are positive. So let's start listing them. I started with the sine last time. The sine of 55 pi over 4 should be negative square root of 2 over 2. Cosine of 55 pi over 4 is positive square root of 2 over 2. Tangent is sine over cosine. They're the same, so that should reduce to 1, but it's going to be a -1 because the cosine is positive, the sine is negative. And now we flip those over. Oops, I just got screwy. There's the secant, it's the reverse of that one. 2 over the square root of 2 simplifies to what? You know yet? 2 square root of 2 over 2, which is just square root of 2, and secant's positive. So the cosecant of 55 pi over 4 should be a negative root 2, and the cotangent should be a negative 1. Agree?
Okay.
So you see how many times the denominator goes in the numerator. If it's an odd number, you start counting from here, plus the remainder. If it's an even number, you start counting from the positive x-axis, plus the remainder. So the important thing is to know those 6 angles in quadrant 1, 0, pi 6, pi 4, pi 3, pi 2. So that's only 5 angles. And then you figure out the quadrants. Okay? Yes, sir.
Could you convert the radians to degrees and just do it that way as well?
Sure. Let's get some practice converting from radians to degrees. And today we're going to do a lot of degrees to radians. So if you're given 8 pi thirds, how many degrees is that? How many degrees is 8 pi thirds, and how do I find out? There's 360 degrees in the circle, and how many radians are in the whole circle? 2 pi radians is the same as 360 degrees. So that means pi radians is the same as 180 degrees. So if you start off with radians, like this one, and we want radians to cancel, then you put pi radians on the bottom, 180 degrees on the top. That way we'll be left in degree measure. So 8 pi times 180 divided by 3 pi. Let's just cancel where we can before we multiply. Let's knock off the pi's. And many of you are asking me how to enter that in WebWord. You just type the word pi. Don't multiply it out on a calculator, just type the word pi. So I got this out, so I canceled this pi with that pi. And I don't have any, or I do have a common factor. 3 divides 18. 3 divides 18 6 times, so 3 into 180 goes 60 times. So all I have left is 8 times 60 degrees. 6 times 8 is 48. Tack on the 0. That is 480 degrees. But when it's in degrees, it's harder to see what your reference angle is, right? You have to subtract 360, then you have to figure out which reference angle you got. Here, you just look at it. It's looking at you right there. Okay. How do you go the other way? How do you convert from degrees to radians? Okay, so I want you to convert 600 degrees to radians. See how quickly you can do that one. Leave pi in your answer. Time glare. It's 600 degrees to radians. That's what's under that glare right there. I don't remember if it helped to shut the lights off in the front or not. See if that's avoid some glare. You guys can't see your notes anymore. It does have for people watching at home. Okay, so to convert from radians to degrees, you multiply by 180 over pi. To convert from degrees to radians, you multiply by pi over 180. Right, that'll cancel the degrees for us. So we can cancel the zeros. 6 goes into both of those. 6 goes into 60 10 times. 6 goes into 18 3 times with the pi left. Is that what you got?
Yes.
Did I jump in too soon? Were you still calculating? Anything else you need to know? Okay. So I'm going to ask a couple of things from you. What is the circumference of a circle if you know its radius? 2 pi r. What is the area of a circle if you know its radius? Pi r squared. So I'm just going to look for part of the circumference and part of the area of a circle. So I'm going to take a whole circle and I'm going to form a central angle. That's an angle from the center, and cut off a sector of the circle. And in that sector of a circle, I'm interested in how long that piece of arc is, and I'm interested in the area of that whole thing. So that's what we're going to do in section 3, 2. We're going to get arc length and area of a sector of a circle. Zoom out. Yes, length and area of a sector. Turn it there here. Oh, so what you just told me was the circumference of a whole circle. Circumference. That's a tough one to spell. Of a circle of radius r is given by circumference is 2 pi times r. And that the area of this same circle of radius r is area is equal to pi r squared. Circumference is linear units, as if you were about to build a fence around a circular lot. Area is square units. I won't worry about that just yet. What we're going to be working on is if I have an entire circle, here's the center of that circle. Maybe I know the radius, and I just cut off part of the circle from here to here. Then I'm interested in finding how long this arc is. That's what I mean by arc length. We're going to denote the length of an arc with a lowercase letter s. And then we're going to want to know what this area is in here. And what we will know is the angle right there. So I'm going to appeal to your common sense. Suppose I know that I have a circle and I look at a sector cut off by an angle of measure pi over 4. Pi over 4 cuts off what fraction of the whole circle? A quarter of the pi, but a circle has 2 pi in it, right? So pi over 4 is 25% of the top, 25% of the bottom. So I've got pi over 4 is 1/8 of an entire circle, right? So if I know the circumference of a whole circle, then the circumference of the pi over 4 sector is 1/8 of that. If I know the area of the entire circle, then the area of that pi over 4 sector is 1/8 of that. That's a lowercase s. The lowercase s is going to denote arc length. I just made up pi over 4 as an example because I thought that was one you can do in your head, right? Pi over 2 is 90 degrees. And if you cut a circle in 90 degrees, you got 4 segments. Right? So what you do is you figure out what part of the whole circle your angle is cutting off into a sector. And then you take that fraction times those 2 formulas. So if theta is an angle in radians, everything we're doing is in radians. Once you see this pi here, you know you're in radians. So theta is an angle in radians. Then we can figure out what part of a circle is cut off or intercepted or subtended by an angle of measure theta. When we say subtended or intercepted by this angle, we mean just what I said over here. An angle has 2 sides. They hit the circle in 2 points. Those are points of intersection. So it intercepts this arc here, or it subtends that arc right there. Okay? So if you have an angle theta, my example was pi over 4, and you want to figure out what part of the whole circle it is, just set up the ratio. Theta is the part, 2 pi is the whole. So if theta is in radians, then the part of a circle subtended or intercepted by this angle is simply theta divided by 2 pi. And so if I want to figure out S, I just take my circumference and multiply it by theta over 2 pi. If I want to figure out the area, I take my area formula and multiply it by theta over 2 pi. So the arc length is S is equal to theta divided by 2 pi of our circumference, 2 pi r. And the area of the sector is theta divided by 2 pi times pi r squared. That's the easiest way to remember these formulas. But you can see both formulas can be simplified. In this first formula, I've got a 2 pi in the denominator and a 2 pi here. So I can simplify arc length as just being the product between that central angle and the radius of the circle. In this other one, the pi's will cancel again, and I have theta times r squared divided by 2. So whichever way is easiest for you to remember, because they're pretty easy to use. What these two formulas have are 3 parts. The r, the radius of the circle, central angle theta, and then either the arc length or the area. So I want you to be able to use these formulas to find the third piece given any of the two. I'll give you r and theta, you find s. I give you s and theta, you find r. I give you s and r, you find theta. Just remember, every single time you work with this, we're talking about radians. Okay? They're easy formulas to remember. They're easy formulas to use. The only thing that you need to be able to control is keep in mind, we are working in radians. Yes, sir.
So there is no special use where we can use any of those, like for the arc length, I can either use the top or bottom, or just is there a special?
No, the bottom one's for area.
No, I'm
Oh.
sorry, I'm sorry.
No, no, you can use either one. They're equivalent. I just
Great.
simplified here,
Great, thank you.
right? I just canceled the pi's. And here I canceled the 2 pi's.
Okay.
Yes, sir.
Are we gonna work in radians the rest of the semester, or we gonna go back?
We're going to go back and forth and back and forth and back and forth. But most of the formulas that we generate here in chapter 3 are based upon the circle having 2 pi radians in it. Okay, because you don't see a 180 or 360 on here anywhere. Yes, sir.
So if we're switching back and forth, like on an exam, per se, would there be like things like we're dealing in radians, like this section, we're dealing in radians, or are we expanding now?
You have to know.
Fine, okay.
So I said, there's only
No,
one
it's on
thing
here.
that you have to do is just know your part. The easiest way to do is do everything in radians, right?
Yeah.
In calculus, everything's done in radians. How many of you are going to keep going on with calculus? You're the only one going to take calculus? 2. The rest of you are done here with trig?
Yeah.
Yes.
You got some calculus to go.
That's on architecture.
So,
Engineering.
so you are in radians.
That's so sad. I love myself. I love myself. Here's how to never fail calculus. Don't take it.
Okay, so let's find some of them. Let's say we have a circle with a central angle of 5 pi over 8. How about a circle of radius 10 centimeters and a central angle of 5 pi over 8? I want to find the length of the arc subtended by that angle and find the area of the sector subtended by that angle.
You got it.
Got it. So a circle has radius of 10 centimeters. Find the arc subtended by a central angle of measure 5 pi over 8 radians. And then find the area of the sector of this circle. Then find area of this sector. So So I've given you in your circle, central angle means it's always drawn from the origin. Doesn't matter where I draw it. Let's just do it this way now. Let's say that this angle is 5 pi over 8. And it cuts an arc from here to here. The radius is 10 centimeters. That's the length of that ray and that ray. So the arc that I'm talking about goes between these 2 points, from here to here. And the area is this triangular piece. Green never works, but this one did. Look at that. So we make sure we're in radians, our angle is in radians. Then we figure out what part of the 2 pi circle that measurement is. Take 5 pi over 8 and divide it by 2 pi to get the part of the circle we're talking about. 5 pi over 8 divided by 2 pi. Got a fraction on top. Think of that as 2 pi over 1. When you divide by 2 pi over 1, you flip it over and multiply. Right? Pi's will cancel, and I have 5/16 of the whole circle. So if I take 5/16 of the circumference, I've got the arc length S. If I take 5/16 of the area, I've got the area of the sector. Okay? All right, so that arc length. Over again. 5/16 there, so S is 5/16 of 2 pi r, and area is 5/16 of pi r squared. Actually, that's it. Let's do some numbers now. Let's simplify. I have S is 5/16 times, what is that, 25? I'll go ahead and reduce. 16 and 20 are both divisible by 4. So I'm going to replace 20 by 5 and 16 by 4. And then we're done. We've got 25 pi over 4. This is in linear units, so this is centimeters. Where'd the 20 pi come from? I took 2 pi times 10. 2 pi r, 2 pi r circumference. Now I'm down there at the area. I'm going to go ahead and square my radius. The radius was 10. So here's my 5/16 fraction of the circle. And then inside I have 100 pi. Again, 16 and 100 have a common factor of 4. So if I divide the 4 out of each of them, that's 4, and that's 25. So 5 times 25 is 125. Then I got my pi, and then the 4. These are area units, so these are square centimeters. And again, you just enter it just like that in web work,
With,
typing pi for pi.
with centimeters squared, or will that be?
I think the units will be given to you. Okay. I follow that? Okay, so do it again. This time my central angle is 100 degrees. Find the arc intercepted by a 100-degree central angle and find the area of the sector intercepted by a 100-degree angle.
What's the?
Radius is 10. Radius 10 centimeter radius, but now change this right here to 100 degrees. This gave you an additional step to do. Circle of radius 10 is intercepted by a central angle of measure 100 degrees. Find the length of that subtended arc, find the length of that sector. So if you don't want to go to radians, you can go ahead and figure out what part of the whole circle 100 degrees is. How do you do that? You don't want to convert that to radians. What part of the whole circle is 100 degrees? Over half. Let me give you the exact part. It's under half. Not quite half. What part of 360 degrees is 100? 100 over 360 is 10 over 36, or 5 over 18. It's 5/18 of a circle. So you can just use the 5/18 the way I use the 5/4 over there, or the 5/16 over there. You don't want to convert it to radians. That'll give you the same kind of deal. Right? Instead of dividing by 2 pi, we divide by 360 degrees. Write that as a fraction, and then multiply. Would you get the same thing if you convert that to radians? If you convert that to radians and divide by 2 pi, are you going to get 5/16 of the whole circle? Let's do it. Let's convert it to radians, just for funsies. How many radians is 100 degrees? Do that right here. We're going to convert 100 degrees to radians. So we take our 100 degrees and multiply by what? Pi over 180. So I can cancel a 0 in the degrees. 10 pi over 18 gives me 5 pi over 9 radians. So then the next question is, what part of the circle is 5 pi over 9 radians? Well, you divide 5 pi over 9 by 2 pi. So 5 pi over 9 divided by 2 pi is 5 pi over 9 times the reciprocal. The pi's cancel, and there's the 5 over 18. That's 5/18 of a whole circle. Just like we got when we took 100 degrees and divided it by 360. So either way you want to look at it, find the part of the whole circle represented by the sector, then multiply it by either circumference or area, depending on which one you want. So for arc length, S is going to be 5/18 of 2 pi r. R was 10. For area, area is going to be 5/18 times pi r squared. Area It's 5/18 times pi r squared. Yes, sir.
Would we leave it like that on, like wet work or on an exam? Or do you
Yeah,
want
that's
to-
fine. But we're not scared of numbers, are we? I picked nice whole numbers for you like that, so we can do them. I'm not making you multiply by 513 or something. Because look, I can divide 2 into 18 and get us a 9. 5 pi times 10 is 50 pi divided by 9. So S is 50 pi over 9 centimeters. Over here again, I get 100. So 118 are both divisible by 2. So this becomes a 50 pi over 9 times 5 is 250 pi over 9 centimeters squared of area. Agree? So when you know the angle, that's kind of easy. Now let's knock off some of these and see if you can do it in different orders. So here's a picture. I want you to find R. In blue, coloring this part. Well, let's figure out what length that is. Let's say that that has a length of 24 pi. There to there. And so now let's make up an angle. Let's see, it looks like it's a bit more than 180. So let's say that that's 200 degrees. 200-degree central angle. 24 pi is the length of the arc. What is R? Where do we start?
You can use equals, you can use S equals the record signal multiplied by the radian.
Okay.
Radius, you can use that.
S is R theta or theta times R. If we're going to jump right to there, we got to put theta in radian measure.
Right.
Right, so let's go ahead and convert 200 degrees. So you can knock off a 0 anywhere, and you've got 20 pi over 18. 20 pi over 18, they're both even numbers, so knock out a 2. 10 pi over 9. You happy with that for theta? So we know this number. We're looking for that number. We know this number. So let's put our numbers where we know them. 24 pi on the left-hand side. 10 pi over 9 for theta. And we're solving this equation now for R. So what's next?
Get the reciprocal of the rectangle and radians, and you multiply it by
Okay.
24 pi.
So let's take 9 over 10 pi, that's the reciprocal, times 24 pi. And that's going to be R. So in other words, we're dividing by 10 pi over 9. But you divide by 10 pi over 9, you multiply by the reciprocal. And then simplify by canceling the pi's. I'm going to go ahead and divide both of these by 2. So make that 12 and make that a 5. So I have 9 times 12 divided by 5 is equal to R. 9 times 12 is 108. So R is 108 over 5. Okay. So good? I think I put one of these on your web work. Let me see. We'll do a different one first before I jump. Okay, this time let's go with a circle of radius 2. I don't know, I guess I'll stick with centimeters. Circle of radius 2 centimeters. And we've got a sector that cuts off 3 square units of area. So 3 centimeters squared of area. Find this angle theta. Central angle theta is unknown, but we do know it cuts off 3 square units of area in a 2 centimeter circle, radius circle. Is that enough information for you?
Yes.
So if you want, you can start with the simplified formula here. Area is theta times r squared over 2. Put your numbers in where you know them and solve for theta. Okay. So area we have is 3. Theta we don't know. R is 2. We're solving this equation for theta. So 3 is equal to 4 theta over 2, says 3 is equal to 2 theta. So theta is 3/2 radians. Well, how big is 3/2 radians? I asked you to draw an angle and measure 3/2 radians. How big is pi radians?
3.14.
3.14. So how big is pi halves radians?
1.7.
1.57. 1.57 is pi halves. So pi halves simplifies to roughly 1.57 radians. This is almost a 90-degree angle, not quite, right? Just short of being a 90-degree angle. So even though there's not a pi on it, we can still measure length around the circle. Pi is a multiplier, so I can approximate it. Okay? Yes, sir.
Can we leave it up to the next?
Uh-huh. You can. I just wanted to make sure that you understood, even without a pi, that's an angle measurement.
Will allow us to just be in the radians.
Uh-huh. Rubric will want it in the radians, unless it says, put it in degrees.
And do we type radians?
I think that if you just do the 1.5, I think you're fine. If you look at a globe is divided with these, I guess, what would those be? Vertical lines and then the horizontal lines. Vertical lines are called lines of longitude, and the horizontal ones are lines of latitude. Agree? Have you heard of that, latitude?
Yes.
Well, we could use latitude measure to measure distance between cities. Because the latitude kind of cuts the globe up in terms of arc length. So let me write down what I just said. Latitude is the measure of a central angle let me see if that's visible. Latitude gives the measure of a central angle with vertex at the Earth's center the initial side goes through the equator and the terminal side goes through the latitude line. Goes, I need an O in here. Good gosh. So the equator corresponds to our x-axis. So let's flatten the globe just to a circle. And here is the center of the Earth, and there's the equator. And suppose we have a city here whose latitude is given as some sort of measure. Suppose the latitude here, for example, is 40 degrees north. So that latitude bar runs circular, but it's 40 degrees north of the equator. So essentially that's telling you that this is 40 degrees. But if you look on the globe, that's a line that's coming around, going around like that. The equator corresponds to 0. Okay. So let's use this. We can use this. Use latitude to find the distance between two cities if we know their latitude measure. But we'll need to know the radius of the Earth. So let me see what your book uses. Most of the times it's 6,400 kilometers. And your book uses that. Ours is 6,400 kilometers is the radius of the Earth. All right, so let me grab us an example. The city of Erie in Pennsylvania. Ooh, how do you spell Pennsylvania? Can you spell Pennsylvania? Makes you glad you don't live in Pennsylvania, doesn't it? Erie, Pennsylvania is approximately due north of Columbia, South Carolina. Let's say the latitude of Erie is 42 degrees north. And the latitude of Columbia is 34 degrees north. Using that 6,400 kilometers as the radius of the Earth, find the north-south distance between the two cities. I'll draw a picture while you guys are writing that down. Picture is this. Here's the Earth. Here's the equator coming across. And I know this is 6,400 kilometers of radius. If I go up from there 42 degrees, just so you can see it, let's make this 34 degrees to put us at Columbia. So this angle is 34 degrees. And now go up 42 degrees. And that city is Erie, and that's this angle. Let's get another color in there. So that one was 42. Color that works. Our job is to find the distance between the two cities, which is right here. See that? You guys can't even know that. And for this little length right here, you know, this arc is subtended by a 42-degree angle, and that arc is subtended by a 34-degree angle. So if I've got 42 degrees there and 34 degrees there, can you tell me what angles between the two dotted lines? 8. 42 minus 34 is 8.
Yes.
So that's this angle in here. So essentially, I'm asking you to find the arc subtended by an 8-degree angle. Find the length of an arc subtended by an 8-degree angle. What do you do?
Multiply the new reference angle by 64.
Okay, but what about the fact that that's 8 degrees?
Oops.
Let's convert it to radians. So I do what to convert that to radians? 8 degrees times pi over 180. So those are both divisible by 4. So 4 goes into 8 twice. 4 into 18. So 4 into 180 goes 45 times. So 2 pi over 45 is that central angle. And so arc length is r times theta. So r was the 6400, theta is 2 pi over 45. S is equal to r times theta, theta times r, doesn't matter which way I say it. 6400 times 2 pi over 45. I'm not going to reduce anymore. I'm going to go ahead and give this to you as a decimal because it's in my book. That's roughly 890 kilometers. All right, my next one. You know, back in the old days, cars had their windshield wipers with the pivot mounted on the top. Yours now goes like this, or some fraction of a circle. When cars were first made, they had windshield wipers that pivoted back and forth like that through a central angle. So they subtended portion of a circle. So suppose we've got a car where the blade holder of the wiper holder is, let me use the numbers in your book, 10 inches long, but of that blade, only 7 inches of it consists of the rubber part that is the wiper. How much of your windshield area is cleaned by that wiper? Is what I just said. So the windshield wiper is affixed to a 10-inch blade, but only 7 inches of it consists of the little rubber part that rubs across your window. And that sweeps back and forth. We'll give you maybe an angle here. So let's say that that angle that it sweeps out is 95 degrees. So since there's the rubber part's the only part that can clean the windshield, there's a piece of your windshield that's not getting cleaned. So I've got this little ring here that's being swept out by the windshield wipers. I want to know the area of that ring right there. This is a windshield wiper. What is the area cleaned or wiped by this 7-inch blade. So this is the only part that touches the windshield. The other part is just the arm of the blade that moves it. Somebody talk me through a plan. Yes, sir.
I'm going to subtract the area for 10 inches, and then I'm going to subtract the area from the area of 3 inches.
That's right. To get this 7-inch area here, pretend that you're wiping a 10-inch arc area out, but 3 inches of that 10 inches doesn't wipe anything. So we want to find the area of the 10-inch one minus the area of the 3-inch one. Both of them have a 95-degree angle. Okay, so those represent radii, right? That's a 10-inch radius, that's a 3-inch radius. So area is pi r squared. We just have to figure out what fraction of the circle 95 degrees is. So we can do that in degrees if we just divide 95 by what? Which, keep it in degrees if you want to just find the fraction of the circle. Divide by 360. So let's figure out what 95 divided by 360 reduces to. Both of those are divisible by 5. Let's see, 5 times 1 is 5, leaving me 45, so that's 19. 5 times 7 is 35, leaving me 10. So that's 1972, 19/72 of an entire circle. So if I use that as my multiplier in front of my pi r squareds, I'll find the pi 10 squared times that number minus pi 3 squared times that number. Does that make sense? It's a common factor, so let's just factor it way out front. So pi times 10 squared minus pi times 3 squared. Well, the pi is a common factor, so I can pull that out. So I can make it 19 pi over 72. And then find 100 minus 9. 100 minus 9 is 91. And there's some numbers I don't want to multiply out, so let's just call that square inches of area. Does that make sense to almost everybody? Didn't make sense at all? Where did I lose you? Did you understand that we're making a ring of a circle? Suppose I have a whole circle here of radius 10 and a whole circle here of radius 3. So do you agree the part in the middle of the ring would be just 7 inches of that? So now don't look at that whole picture, just look at a 98-degree sector of it. So if I, from here, measure a 98 degrees, so all the way across is 180. So if I just cut it up into here some bit to 98 degrees, I've got that picture up, 95 degrees. I've got that picture upside down. So the first thing I did is I found the area without the hole in it. Pi times 10 squared. But then I multiply it by 95 over 360, so I only get that part of it. Then I found the area of this little one. That was pi times 3 squared times that part of it. And then that leaves what's outside. I just did some factoring so I wouldn't have to mess with the numbers. Okay. Okay, what we are going to do next is more with the unit circle. In section 3.3, we're going to define our functions in terms of points on the unit circle. Now, S is the length of an arc, right? S is R times theta. And we've been using the unit circle. So what is R? 1. So if we're on a circle of radius 1, the length of the arc between the angle measures is the same as the angle measure. S is R times theta, but R is 1. So S is theta. So if I know the length of this arc here, and I then can find the sine of that length, because it's the same as the sine of that angle. I can find the cosine of that length, because it's the same as the cosine of that angle. So in the unit circle, that central angle and the length of the arc are the same. So when I say find the sine of S, if S is pi over 4, well, that's the same as saying find the sine of the angle pi over 4. Square root of 2 over 2, right? Just putting you on the unit circle instead of on any circle at all. So what I'd like you to do between now and Tuesday is maybe get that unit circle memorized. Bring it with you. There are blank copies on Blackboard, and you can practice labeling all those ordered pairs, so that when I ask you to find the cosine of 11 pi over 4, boom, you know what it is. Okay? All right, I guess you want to go. Have a marvelous weekend.